So hello everyone, welcome to the channel. So in this video I'm going to show you the advanced flood hazard zonation and risk profiling using a GloFAS dataset in Google Earth Engine. So now let's get started. So flooding represents one of the most devastating and recurrent natural hazards globally, with a profound impacts on human settlements, infrastructure and economic stability. The coastal regions and low-lying urban areas such as Houston, Texas are particularly vulnerable due to their topographic characteristics, high population density and exposure to extreme weather events. So including the hurricane and heavy precipitation systems, the traditional flood assessment method often faces a limitation in the spatial coverage, temporal resolution, and computational efficiency, so creating a critical gaps in the comprehensive flood risk management. So the study presents an integrated framework for advanced flood hazard zonation and risk profiling by leveraging the computation power of Earth Engine and the sophisticated hydrological modeling capabilities of the global flood awareness system GloFAS dataset. So the implementation focuses on Houston, the metropolitan region and surrounding Gulf Coast areas. So a region historically susceptible to catastrophic flooding events as demonstrated by Hurricane Harvey in 2017. So the methodology encompasses a systematic approach to flood risk assessment through multiple analytical dimensions. Starting with the core implementation begins with first we're going to delineate our suitable study region of our choice. So once we defined our region of interest, our next step we're going to access the GloFAS flood hazard repository dataset. So the framework extracts a pre-modeled inundation depth data across multiple return periods of 10, 20 and 100 years of flood events, representing a varying probability of flood occurrence and intensity. So a dynamic data processing pipeline ensures an efficient extraction and mosaicing and transformation of these flood layers, incorporating the intelligent band management and spatial clipping operations to optimize the computation performance. And next is the analytical workflow advance beyond the simple visualization through the implementation of a multi-phased assessment technique. A sophisticated cartographic rendering employs a specialized color set to communicate the flood depth variation, and while statistically analyzing that quantifies the spatial distribution of the inundation patterns through the histogram profiling. And further, the methodology incorporates a zonal statistics to calculate the total inundation area for the specific flood scenario, providing a crucial metric for emergency planning and infrastructure development. So a comparative analysis between a different return period reveals an incremental flood depth increase, highlighting the areas most vulnerable to extreme hydrological events. So now let me get back to Earth Engine. So in our first step, we're going to define our region of interest. For example, we're going to specifically select Louisiana as one of our study region of interest. So I'm going to select my study region here. So you can able to see this is my region of interest. So we're going to take the coastal part of the study region here. So as I mentioned earlier, so to create a region of interest, first let me delete my existing variable. So once you did the next step, to create a study region of your choice, navigate to this option called draw a rectangle. And now I'm going to draw a rectangle over the coastal part of the study region. So in the Louisiana, so towards the coastal part of New Orleans. So we're going to draw my study area here towards the coastal part here, covering all the coastal part. So once you draw your region of interest, next step I'm going to click this option called exceed. And the top section, a new variable emerges called variable geometry, and in that we're going to click this option called show generated code. And I'm going to copy the latitude and longitude of this particular study region here using Ctrl+C from my keyboard. So we're going to copy this latitude and longitude. So this is our study region of our choice. So this is the latitude of our study region, latitude and longitude of our study region. So once you copied it, we're going to paste it inside this particular variable called region coordinates. So we're going to paste this particular value inside this variable called variable region coordinates. So we're going to paste using Ctrl+V. So once you pasted your latitude and longitude inside the variable region coordinates, so in the next step we're going to create a geometry object from the coordinates to define our study region. So to do that, we're going to mention a variable called analysis boundary is equals to earthengine.geometry.polygon. So we're going to convert this variable containing the latitude and longitude into a polygon. So referring to this particular variable called region coordinates, so which holds my latitude and longitude of my study region. So now it's going to convert it into a polygon. So in the next step, we're going to set the suitable zoom level of our choice here. So to create a suitable zoom level, I'm going to mention map.center object, and I'm going to mention the variable name called analysis boundary. So we're going to mention the name as analysis boundary with a suitable zoom level of 7. And the next step, we're going to import and filter the GloFAS flood hazard dataset into Earth Engine. So before that, let me go through this particular dataset here. So the global river flood hazard maps are a gridded dataset representing the inundation along the river network for 7 different flood return periods from 1 in 10 years to 1 in 500 years. So the input river flow data for the new maps are produced by means of an open source hydrological model, while the inundation simulations are performed with a hydrodynamic model, example the list flood FP, and the extent compresses the entire world with the exception of Greenland and Antarctica and small islands with a river basin smaller than 500 square kilometers of area. And the cell value, which indicates water depth in meters, and the map can be used to assess the exposure of population and economic assets to the river floods and perform a flood risk assessment. So the dataset is created as a part of the Copernicus Emergency Management Services. And the dataset availability is given here from 2024 to 2024, and the dataset provided is Joint Research Center, and using this code you can access this particular dataset here. So now let us go through the bands. So these are the following bands that is available in this dataset here. So the pixel size, the resolution of this particular the dataset is around 1000 meters, that is 1 kilometer, and the units is in the meter. So there is only one band that is available inside this dataset called depth, and the unit is in meters, and the minimum value is around 0.1 to a maximum value of 9494.89, and the pixel size is in meters, and the description, it is mentioned as a flood inundation depth. So let me get back to Earth Engine. So now to explain about this particular data, so JRC Global River Flood Hazard Map version is a high resolution global map that could answer critical questions for any given location near the major river. How deep could the water or flood water get during a catastrophic flood, and how likely is that a flood to happen? And think of it as a worldwide flood risk atlas created by the European Commission Joint Research Center using the Global Flood Awareness System, GloFAS Dataset. So let me get back to Earth Engine. So to access this particular dataset, to load this GRC Global Flood Awareness System, first we have to define a variable called GloFAS Flood Collection is equals to earthengine.imageCollection JRC SEM GloFAS Flood Hazard version 1. And this dataset contains, what is the dataset is, the dataset contains a pre-modeled flood inundation depth for various recurrence intervals. So using this particular code, we can access those dataset. That is the pre-modeled flood inundation depths. So next we're going to filter it based on our region of interest. So to do that, I'm going to mention this function called .filter bound analysis boundary. So this is going to include only images that intersect our study area. So in the next step, so to go through the details about this particular dataset, we're going to mention as print available return period in collection, and we're going to mention GloFAS flood collection dot aggregate array, and we're going to return the return period. So let me run this code here. I'm going to click this option called run. So in the console section, you can able to visualize here we have the return period in collection. So these are the following return periods here, so you can able to see that. So in the next step, we're going to show you what is the return period is. So what is a return period? For example, RP100. So this is the most important concept. A return period, RP, is a statistical measure of probability and often misunderstood as a schedule. So a 100-year return period, RP100, does not means a flood happens exactly every 100 years. It means that in any given year, there is a 1% chance of 1 by 100 of chance of a flood of that magnitude is occurring. So it is a measure of rarity and severity. So the higher return period means the more severe and less frequent flood events. And next is the RP 10 percentage. So the chance of each year, so it is common but it less severe flood. And next is the RP 100. So if it is a 1 percentage, and the chance each year is very rare, and if it happens, it could be very severe flood. And last is the RP 500. So which represents about 0.2 percentage of chance of each year. So it is extremely rare, and if it happens, it could be a catastrophic flood. And similarly, let us take a look at this particular one. So what is the inundation depth? So inundation depth, so this is simply how deep the water could be above the ground level during a flood of a given return period. So it is usually measured in meters. So the inundation depth simply represents the depth of the water could be above the ground level during a flood situation. So that is what is called as the inundation depth. So it's usually its unit is in meters for this dataset. So let me get back to Earth Engine. So in the next step, we're going to create a dynamic data loading function. So basically, we are doing this to creating this dynamic data loading function. So we're going to combine all the images and the filters into one image to clip to our study area in order to reduce the processing time. So to do that, we're going to create a function called load flood depth data, and we're going to mention the return period and the period label. And in the next step, we're going to filter the image collection for a specific return period and create a mosaic. So to do that, we're going to mention a variable filtered image is equals to GloFAS flood collection. So we're going to filter it based on a specific return period. For example, I'm going to mention dot filter earth engine dot filter dot equals to return period is return period is equals to return interval. And the next step, we're going to mosaic, we're going to combine all this image together, so using dot mosaic function. And last, we're going to clip it based on our region of interest using dot clip function analysis boundary, which is our study region. And the next step is to ensure we have the earth engine image object. So to ensure we have an earth engine image object, first we're going to define a variable called the processed image is equals to earth engine dot image filtered image, referring to this particular variable we created earlier for this function here. And so in the next step, we're going to dynamically get the first band name. So to do that, we're going to mention the variable called primary band name is equals to the processed image dot band name function dot get 0. So we're going to get the first band name. And the next step, we're going to select and rename the band for the clarity. For example, we're going to mention the variable called depth data is equals to image processed image. So in that, referring to this particular image, so processed image, we're going to mention this function dot select the primary band name. And we're going to rename using this particular rename function dot rename inundation depth plus the period label. So it's going to output with the inundation flood inundation depth plus the return period, that is it might be of 100, 10, 220 or 500 as a return period. So that is mentioned as a period label. And last, we're going to return as a return depth data. So it's going to return this particular data, that is depth data. And next step, we're going to execute the data loading for multiple return periods. So we're going to load our flood depth data for 3 significant return periods, starting with the 10 years of return period, and next is the 20 years of return period, and followed by 100 years of return periods. So to load the flood depth data for 3 significant return periods, which includes a variable like decadal flood depth is equals to the load flood depth data, referring to this, so which is referring to our function which we created earlier here. So referring to this particular function here, that is load flood depth data. And in the next step, we're going to mention the return period here. So we're going to mention the return period as a 10, so which represents the decadal, the 10 years of return period. And similarly, in the next step, we're going to define another variable called, so the variable called Vecinal's flood depth is equals to the load flood depth data 20, which is the 20 represents the 20 years of return period, Vecinal's, and which represents this is the 20 years return period. And last is we're going to define another variable called, so the another variable called Centennial flood depth is equals to the load flood depth of flood depth data of 100 years of return period. and it could be represented as centennial of 100 years of return period. And next step, we have to configure the visualization parameter in order to visualize the in a different color tone. So we have to using this visualization parameter, we can visualize the high flood areas, high flood depth areas versus the low flood depth areas. So to set up a visualization parameter, so we're going to create a blue color gradient blue color gradient palette for the depth visualization. So starting with a variable called, we're going to define a variable called the depth color gradient. So starting with the different color tones here. So this particular set of color which represents the lowest flood depth, and this set of color, there is a dark blue color which going to represents the high flood depth areas. So to set the visualization parameter, we're going to mention the variable called visualization params. We're going to set the minimum and maximum values here. So we have a total of 6 color palettes here. So we're going to mention the minimum of 0 and to a maximum 5, which represents the 6 different color palettes. And the palettes, we're going to represent this variable called depth color gradient, which representing this particular variable containing the different color palettes. And last is the opacity. So we can mention the opacity as 0.8, slow, which represents slightly transparent to underlying the, so to visualize the underlying the geographic names. So we're going to mention with the opacity of 0.8. And the next step, we're going to add this multi-layer visualization to the map here. So to add all the 3 flood depth layers with the different visualization options, starting with, we're going to mention map.add layer, decadal flood depth. We're going to mention the visualization params, which represents this particular variable containing the visualization parameters. And we're going to output as flood inundation depth of 10 years return period. And we're going to output in this name here the flood inundation depth of 10 years return period. And the next step, we're going to add another variable called map.add layer. So the layer called bicentennial flood depth. So represent this particular visualization parameter, that is visualization params represent this particular variable, and output the layer name as flood inundation depth of 20 years return period. And last is this, we're gonna add this particular layer called centennial flood depth. So we're gonna mention map.add layer, centennial flood depth, and representing this particular visualization parameter representing this variable. And we're going to output as flood inundation depth of 100 years return period. So now so now I'm going to run this code. I'm going to navigate this option called run, and I'm going to click run script. So let us take a look at this layers here. So starting with, we have the 3 different layers here. The study area, I'm going to turn this off. So the first layer is flood inundation depth of 10 years return period, and followed by the next is a flood inundation depth of 20 years return period. And let us take a look at this particular dataset here. Let me turn this off. I'm going to turn off my geometry polygon which is created earlier. And you are currently visualizing the flood depth for 10 years return period, 20 years return period, and 100 years. So first let us take a look at the flood inundation depth of 10 years. So you can able to see the blue regions. So the blue color which indicates the high flood depth areas. So for example, the study region has a lake here. For example, let me turn to a satellite mode here. So now we can able to visualize it. Let me turn off this. So you can able to see this particular area has some lake here. So this lake, which the dataset clearly indicates the flood depth here. So I can able to see here so certain portions here, for example, so the urbanized area, which includes these are the areas of urbanized area. So I'm going to focus on this set of urbanized areas here. So towards you can able to see towards the eastern part of the region has a darker blue shade, which indicates the high flood depth areas. And in case of extreme flood events, a proper mitigations to be done in those areas here. For example, this particular areas, and you can able to see this areas. Let me turn this off. So this particular areas might be facing a flood inundation during this type of flood events of the 10 years of return period. And have already mentioned what is RP 10 percentages. So the RP10, which represents a 10% chance each year, which represents a common flood events, which is the flood is common, but the severity is less severe flood, which represents the RP10. And the next layer, let me turn on the flood inundation layers of layer called 20 years return period. I'm going to turn this on. So you can able to clearly visualize the difference in this case, in this scenario here. So this is the difference here. So previously during the flood inundation, so this was for the RP10, this was the amount of flood that can possibly can happen. The amount of flood that can cover the flood depth can be this much higher if the, so this blue area which indicates the flood depth areas. So for example, I'm going to use my inspector tool. So I'm going to use my inspector. I'm going to place the inspector tool over this area, and let us visualize the value here. So starting with the flood inundation depth of 10 years, so the possible level of flood depth which might be of 5.31 meters, and in case of flood inundation depth of 20 years return period, so there is an increase in the flood depth of from 5.31 meters to 5.92 meters in case of RP20. So RP20 which indicates RP20 which indicates a 20% chance of each year. So it is common and less severe flood. So compared to RP100, so the chance is 1% chance each year, and the flood is rare, and if it occurs, it is very severe flood in case of RP100. So let us go. This is the difference between RP10 and RP20, RP10 years versus RP20 years. So now let us visualize for the RP 100 years of return period. And this is the RP 100 years of return period. You can able to see all the urbanized areas have been completely covered by the flood water here. So it is loading here. So you can able to see in case of RP 100. So RP 100 as previously mentioned, so 1% chance each year, and the flood is rare. If it occurs, it might be a very severe flood. So you can able to see it covers almost all the urbanized areas here. So in case of RP 100, and in case of RP 20, this is the flood scenario, and in case of RP 10 years return period, this is the scenario. And let me get back to the console section here. So in the next step, we're going to add a study area boundary as a transparent layer for the reference. For example, you can able to see the study area here. So this is our region of interest, and you can adjust this transparency of this layer. So in the next step, to export this high resolution flood depth map to a Google Drive. So for example, I'm going to export the 10 years flood depth data to my Google Drive. So to export this particular image of RP10, I'm going to mention the export.image to drive. So in the image, I'm going to mention is decadal flood depth, and the description I'm going to mention is flood depth of 10 years RP, and the region it is our study region of analysis boundary, and the scale is 1000 meters, and the coordinate reference system is EPSG 4326, and the folder I'm going to mention is flood risk analysis, and last the max pixel value is 1:10 power 13. And in the next step, we're going to perform the statistical analysis for the flood depth here. So we're going to create a histogram to show the distribution of the flood depth. So to do that, we're going to use this RP 10 years return period dataset. So we're going to create a variable called depth distribution chart is equals to ui.short.image.histogram, and the image I'm going to mention is decadal flood depth, and the region I'm going to mention this analysis boundary, and the scale it is of 1000 meters, and the max bucket of 300. And you can set additional options to this particular histogram here. For example, I'm going to set the set options. I'm going to mention dot set options. The title I'm going to mention is statistical distribution of the flood depth of 10 years return period, and the h-axis I'm going to mention the title as flood depth, flood inundation depth, and you can give it a suitable style of your choice. For example, italic you can give it as a true for in case of you want to show this particular chart in italic, and you can use the bold. So we can use either true or false. The true is going to give us a bold, And the v-axis, the title is pixel frequency count. So the title text style, we're going to mention the italic and bold, and you can select the possible colors and legends. And last, to display the chart in the console, I'm going to mention is print depth distribution chart. And in the next step, let us visualize it. I'm going to run this code here, and let us take a look at this particular chart here, the flood depth chart. So this is RP 10 years of written period. So we are currently visualizing this particular axis giving us the flood inundation depth, which is ranging from 0 to 10 meters. And this is the pixel frequency count here, which indicates the number of pixels that falls in the different flood depth classes. For example, so this is the amount of pixel that falls in this particular depth of 3 meter flood depth. So there is a large amount of pixel which falls in this particular class of flood inundation depth of 3 meters. So you can able to see the values here. And similarly, this is the next value which speaks high level of pixel which falls in this value, which is around the flood inundation depth of 3.5 meters. And the lowest flood depth, it is observed to be around I think it is around 7.5 meters. 7.5 meters is the lowest flood inundation depth, but the area which covers is compared to the pixel which covers it is comparatively less. And the highest level of the flood depth which is around 3 meters. So you can able to see from this graph here. And in the next step, I'm going to calculate the zonal statistic for the flood depth area, the total flood depth area. So to calculate the total inundation area for 10 years flood, so we're going to mention a variable called inundation area is equals to the decadal flood depth dot greater than 0.1. So the 0.1 here, which represents greater than 0.1. So it's create a mask in area with a flood depth greater than 10 centimeters of water. So for that, we're going to mention this condition called dot greater than 0.1. So which represents around 10 centimeters. And we're going to mention dot multiply earth engine dot image dot pixel area. So multiply by the pixel areas. And next step, we're going to mention dot reduce region, and we're going to mention the reducer as earth engine dot reducer dot sum function. So we're going to sum up all the flood areas. So for that, we're using the dot sum function. And the geometry we're going to mention is analysis boundary, and the scale is 1000 meters, and the max pixel value is 1:10 power 13. And last, to get the result, we're going to mention dot get inundation depth decadal. And last step, we're going to convert from square meters to square kilometers. So currently the image is in square meters. So to convert to square kilometers, we're going to mention another variable called area square kilometers equals to earth engine dot number inundation area. We're going to divide it by 1:10 power 6. So once we divide it by 6, 1:10 power 6, it's going to convert the square meters to square kilometers. And last, to visualize the calculated inundation area, we're going to mention print estimated inundation area 10 years flood depth is greater than 10 centimeters. And we're going to mention this area square, which represents this particular variable, and in square kilometers. Now we're going to run this code and visualize the estimated the flood inundation area. So in the console section, you can able to see the estimated flood inundation area for 10 years written period with a flood depth greater than 10 centimeters, which is around 9,589.96 square kilometers of areas. So we're going to perform some additional analysis too. So we're going to compare the flood depth across the written period. So we're going to calculate the difference between the 10 years and that is 100 years of written period versus and the 10 years of flood depth. So to compare those flood depth of 100 years and 10 years, so for 10 years of flood depth, we're going to mention another variable called the depth difference is equals to the centennial flood depth dot subtract decadal flood depth. So we're going to rename as depth increases 100 years versus the 10 years. So we're going to mention create a divergent color palettes to show the increase in flood depth. So for that, we're going to mention a variable difference palette is equals to. So these are the following set of different color palettes which indicates shows an increase in flood depth. And we're going to mention the variable called def vis params equals to the minimum of 0 to a maximum of 3, and the color palettes we're going to mention difference palettes. And the last step, we're going to add this difference layer to map. So using map.add layer, the depth difference depth with params, so we're going to output as a additional flood depth of 100 years versus the 10 years of return period. So we're going to run this code and let us visualize this result here. And going to navigate to the layer section. I'm going to zoom this. So we can see the comparative analysis between the RP10 versus RP 100 years. So we're going to turn this off. And we're going to turn on the additional flood depth 100 years versus the 10 years return period. So let us visualize the result. So let me turn to a satellite mode here. So we're going to navigate to the layers. I'm going to click this option, and in the custom section I'm going to make sure that you click this option called stretch 90%. And once you've applied it, I'm going to mention apply here. So you can able to see the value ranges from minus 1.1202 to the positive 3.1411 meters. So all the blue areas which indicates the, so this particular image which shows us the increase in the flood depth. So from this image you can able to see, so all the increase in the flood depths are indicated in this color, in this blue color. For example, this particular portion of this area which shows us the flood depth area has been increased in this area, and comparatively the other part of the study area which doesn't show any significant rise in the flood depth. So the majority of the study area which shows us a increase in the flood depth here, but comparatively this particular area has a very high flood depth area, and even the flood depth is also decreased in certain part of the study region, which is indicated in this set of colors starting with the red and orange color. So which clearly indicates these areas where the flood depth has been decreased. Comparatively, the blue areas which shows us the flood depth has been increased. So from this particular part of the sector of the study region, which shows that the flood depth has been increased based on the RP100 versus RP10. So let me close this. So now let us look at the few details about this particular data set here. So starting with who uses this data and why. So for example, the most users will be the urban planners and government agency to create a flood zoning maps to restrict the construction in high risk areas and plan infrastructure, and disaster management teams for emergency preparedness and response planning, identifying the evacuation zones and pre-repositioning resources, and the insurance company to assess the risk and set the premium for the flood insurance policies. And next is the financial institutions and investors to understand the climate related financial risk to the assets and the investments. So for example, a factory which is built in the floodplain. And next is the researchers and climate scientists, so to study the impact of the climate change on global flood patterns and risk. And the last is the international aid organization to prioritize the resource and support for the vulnerable countries with the high flood risk. And the limitation to be kept in the mind when you are using this particular dataset. So the resolution is around 1 kilometer by 1 kilometer, that is 1000 meters. So it is excellent for regional planning, but may miss a very localized flooding details. For example, a street. So it primarily focuses on riverine flooding. It does not cover the coastal flooding from storm surge or the sea level rise. So it covers the pluvial flooding, the surface water flooding from intense rainfall that overwhelms drains like urban flash flood. And last is the snow melt flooding. So if you are using this particular dataset, you have to keep this set of things in you before using this set of dataset for interpretation. So this dataset is not a forecast of flooding happening right now. Instead, it's a global library of pre-model flood scenario based on the probability. So it answers the critical questions: if the flood of a given severity were to happen, which area could be flooded and how deep could the water be? And think of it as a series of risk maps, and each corresponding to the different severity of the flood events, from the relatively common to extremely rare. And last is the cities with the frequent and severe flooding. So these are the major urban centers that experience the regular and often catastrophic flooding due to their location, topography, and climate. So starting with Mumbai, which that is India, the monsoon rains outdated drainage, sea level rise, and urban sprawl over the wetlands and mangroves. So which is a key cause of the flooding. And Dhaka, Bangladesh, located on key cause of flooding, located on the low-lying floodplains of Ganga Delta, intense monsoon rains and river flooding. And next is the Bangkok in Thailand, built on a swampy land and sinking rapidly. That is due to the subsidence and threatened by the Chao River overflow and storm surges. And next is the Jakarta, that is in Indonesia, the world's fastest sinking city, up to 25 centimeters per year. The major causes is the groundwater extraction and weight of the building and sea level rise. And next is Lagos, which is Nigeria. So the low-lying coastal line, heavy rainfall, poor drainage system, and rapid and unplanned urbanization. And last is Texas, USA, the flat topography, clayey soil, and intense rainfall from storms and hurricanes. So urban sprawl within impervious surfaces prevents the water absorption. And next is Louisiana, which is in USA, the built below the sea level on the drained delta land, so which relies on a massive system of levees and pumps to keep the water out and highly vulnerable to hurricane. And last is China, the Pearl River Delta location, the typhoon and storm surges and significant sea level rise threat. And Venice, Italy, the famous for the Acqua Alta, the high waters, so the flooding caused by the sea level rise and land subsidence and high tides. So now let me get back to Earth Engine. So in this video I have shown you the advanced flood hazard zonation and risk profiling using the GloFAS dataset in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like.